Section 7. At this point in the course, we turn a page and go on to a new section of the course. The first section, remember, is all the miscellaneous background information that you need so that the concepts we're going to talk about will make sense. I call it the basics here. The next part of the course, section 7, 8, and 9, well, you can call it the theory of statistics if you like. We're still firmly in the world of probability. Well, a word on that for a second. Statistics is probability done backwards. So probability said, here are the rules, you're about to do something, what's the probability that you're going to get this, that, or the other? So for the time being, we're still firmly in that kind of a problem. In other words, we're looking at probability distributions. We're looking at patterns of randomness, as we, having introduced the concept in sections 5 and 6. Statistics ultimately is probability done backwards, in the sense that we have just done the random thing. We have gotten what we've gotten, although we could have gotten something else, and from that we're trying to recover the actual rules. So probability says a coin is fair. What's the probability that you're going to get at least 60 out of 100 heads? Statistics says, okay, you've tossed a coin 1,000 times. You've gotten 550 heads. What can you conclude about the nature of the coin from that? So that's a lot harder. Thinking about statistics, thinking about probability backwards, well, thinking about it forwards is hard enough, right? Thinking about it backwards is not going to make any sense until we've talked about these concepts. Just for an overview, if you flip a coin 1,000 times and you get 600 heads, you don't really have any context for that. You don't have any context for what you can conclude about the coin from that until you know what a coin flipped 1,000 times was likely to do. So, in other words, you've got to know how the probability is distributed before you know what you can conclude from what we actually get when we do the random thing. So we're still firmly in the world of probability here, where we know the rules and we're about to do something random, and we're looking at the probability we get this, that, or the other. Probability distributions. Section 7 will be an overview of the concepts here in wordy form. That is to say, conceptual form, the ideas involved. Any math that we do in section 7 is sort of beside the point. It's just to illustrate the concepts. And the same applies to some of the notations that we'll use. In sections 8 and 9, we'll supply a little mathematical detail for the ideas that we overviewed in section 7. So I think it'll be less intimidating that way. If you understand that all section 8 and 9 is doing is supplying mathematical detail to the ideas we talk about in section 7, then you'll find them a little less intimidating. Let's get the ideas out of the way first, and we can concentrate on the math in sections 8 and 9. So, section 7, Introduction to Statistics. Again, major concept review. Once again, these pages were originally meant to review things we would talk about in class in more detail. So, hence the videos. Well, again, this section serves as a non-mathematical overview to sections 8 and 9. It's conceptual. So, you get the basic idea of any statistics course. You want to know what's going to happen in an election, you poll 1,000 people. Why do you poll 1,000 people when it would be easier to poll 5 people? Well, we'll find out. But common sense sort of tells you the answer. At the other end of things, why don't we ask everybody who they're going to vote for rather than doing a poll? Well, again, common sense tells you the answer. We've talked about that in the past. So, in order for any of these ideas to make sense, you've got to draw the distinction between the people or things that you'd like to have a piece of information about, all possible voters, the height of everybody in the world, but which is never going to happen, and the ones that you actually look at and examine. This is the idea of the population and the sample. So the population is all of the individuals that we want info about. Well, And, well, I'm not ending a sentence in a preposition because it's not a sentence, right? But all of the individuals about whom we want information. So the heights of everybody in the world vis-a-vis their heights, everybody in the world vis-a-vis what eye color they have, all the calculators in the warehouse, or all the calculators that could ever be made, or ever have been made, or ever could be made, if you want to think of it that way, as I said, vis-a-vis whether they're defective or not. Everybody in the United States vis-a-vis whether they're left-handed or not, anything along those lines, people, info. But of course it's too much. You can't ask everybody in the United States whether they're left-handed. You can't ask everybody in the world what their height is. You can't inspect every calculator that the factory produces to see whether it works or not, and so on and so on. So you have to look at a small, hopefully representative sample. The key word there is hopefully, as in no guarantees. So the sample is the part of the population actually examined for information. The heights of the people picked from the world that you actually measure. The people in the United States that you actually ask whether they're left-handed or not. The calculators in the warehouse that you actually inspect to see whether they're defective or not. And so on and so on and so on. Now the thing to remember about samples is that they never take any noticeable bite out of the population, right? If they do, we've got bigger problems when we go to do the math later. But they don't. That's the point, right? If you could ask 5% of the people in the United States whether they're left-handed or not, well, get 19 friends to help you and ask everybody. The point is you can't. You can ask a lot of people whether they're left-handed, 5,000, but it's still nothing compared to the hundreds of millions in the United States, right? That's important because so many of our formulas are based on this idea of independence, of what we've taken away not really changing what remains to any noticeable degree, so that effectively we've got the same rules every time we pick. Again, that's the beauty of it. Because the sample is so insignificant compared to the population, you wouldn't be doing it if it weren't. Because the sample is so insignificant compared to the population, we have the same rules every time we pick, whether we put back or not. With replacement, without replacement, it's all meaningless. If you take 5 marbles of various colors out of a sack of 12 marbles, then it matters very much what you've taken away and what you've left behind, right? But if you take 5 marbles out of a huge vat of millions of marbles, then it really doesn't matter, If 20% of the marbles in the vat were red, then that's effectively still true after you take out 5, right? So, close enough. In the real world, there's such a thing as close enough to independence. With replacement, without replacement, we don't care. The sample is negligible. It can be big in itself. 5,000 people picked from the world is big in one sense, small in another. It can be big in and of itself. It can be lots of people or things, but it is negligible compared to what we're picking from. That is, number one, important because it makes our formulas work, and more on that in the following sections. But number two, inevitable, because you wouldn't be sampling if you could examine any noticeable bite of the population. But our books make things way too complicated in their efforts to be, one, complete in the sense of mindlessly complete. That is, number two, they want to impress the... Again, textbooks are never written for you. They're written to impress other professors, right? So they tend to be mindlessly complete. And they talk about population size and so forth and so on. For what it's worth, when they talk about it, they generally use capital N for population size and lower n for sample size. But the point is, populations are too big to have sizes. As far as picking 5,000 people from the world goes, the number of people out there might as well be infinite, right? Because it's orders of magnitude more than 5,000. That's important, right? If you flip a coin 40 times, that is to say, if you pick 40 coin flips from all possible coin flips, half head, half tail, fair coin. If you pick 40 coin flips from all possible coin flips, then effectively you have a 1/2 chance of getting ahead each of the 40 times you do it, right? Because you're not taking away enough to make a difference. Because the coin remains the same, the rules are the same the first time, the second time you flip the coin, and so on and so on and so on. I mean, unless you get super sarcastic and say that eventually you're going to erode the surface of the coin, pretty much forever you flip the coin, you're going to have a 1/2 chance of a head and a 1/2 chance of a tail, right? On the other hand, if you pick 40 people from the world, then effectively you've got a 1/2 chance of a male and a 1/2 chance of a female every time you pick, right? Because taking 39 males or 39 females away from the world in the worst case and laying them to one side doesn't really change the fact that half the people left are male and half the people left are female, right? So it really doesn't matter whether our population is theoretically infinite, all possible flips of a coin, or whether it's just incredibly big, 7 billion people. For all practical intents and purposes, any number of people that you could actually look at and examine, 10,000, for all practical intents and purposes, there's an infinite number of people out there, right? 7 billion might as well be infinite. Populations, by definition, are too much. Populations, by definition, might as well be infinite. They are orders of magnitude bigger than what we're actually sampling. If they're not, we have much bigger problems, but of course they are, because that's why we're sampling in the first place. In the real world, I mean when we get to the practical part of the course, so just start thinking in those terms now. Keep it simple. The parameter, then, is the number that is a number describing a population. That can play out in all kinds of ways, and we'll do some examples in a minute. What proportion of everybody in the world has blue eyes? The average height of everybody in the world. Now, bear in mind the one is categorical, blue eyes are not, and the other is numerical, heights of people. But both of the things that we get from them are numbers, right? Proportion of people in the world who are blue-eyed, a number. Average height of everybody in the world, a number. So there's different kinds of numbers, and we'll talk about that as we go. But a parameter is a number describing a population. You can think of it as the rules, you can think of it as the general principles, you can think of it as the number that describes everything out there, the number that describes everything you could pick, everything you're picking from. And then the statistic is the corresponding statistic is the number describing the sample. The height of the people you actually measure, the proportion of the people you look at who have blue eyes, the proportion of the people you pick from the United States to examine who turn out to be left-handed. And again, some populations are a bit more theoretical than others, right? If you flip a coin 50 times, then you are picking 50 coin flips from the population of all possible coin flips. Now, if it's a fair coin, then 1/2 of all possible coin flips are heads. And as for the 50 coin flips you actually do, well, what proportion of them are heads? Well, flip them and find out. So this gives rise to 4 archetypal examples. This works better in chart form, but here goes anyway. We have two dimensions here. On the one hand, we have theoretical versus actual populations, and we'll talk about that. We've talked a little about it. And on the other hand, the other dimension would be there's all kinds of statistics, but the two major ones that we're going to talk about going forward are the proportion of yeses, we'll talk about that in section 8, and the average of the numbers, we'll talk about that in section 9. So I'll put these two together, and it gives rise to 4 archetypal examples that pretty much bring in one sense or another, every other type of example we could do, at least for the foreseeable future. So if we're talking about an actual population, then for instance, you could be talking about the population of everybody in New York State. And then the parameter could be the proportion of everybody in New York State who are left-handed. Population, parameter. Population, everybody in New York State. Parameter, the proportion of everybody in New York State who are left-handed. Then if you pick 100 people from New York State, that's your sample. And then the corresponding statistic would be the proportion of the people, the proportion of the 100 New Yorkers you pick who are left-handed. All right? Let's say that 10% of people in New York State are left-handed for the sake of argument. Well, 10% of millions, right? 90% of millions. So there are millions of people out there to pick who are left-handed, and there are millions of people out there to pick who are right-handed, right? So when you pick 100 with major room to spare, when you pick 100, you could certainly get 100 left-handed people or 100 right-handed people, right? So effectively, the proportion of the New Yorkers whom you pick who are left-handed could be 0 or 1, right? Effectively, it could be pretty much anything between 0 or 1. More specifically, it could be 0 over 100, or 1 over 100, or 2 over 100, or 99 over 100, or 100 over 100. All of them are left-handed. Now, probably it'll be about 10%, and we'll worry about that later. But theoretically, it could be anything. Common sense tells you there's no reason in the world you couldn't pick 100 people from New York and have all of them be left-handed, proportion 1, or all of them be right-handed, proportion 0, left-handed. So effectively, it could be any number between 0 and 1, by which I mean it can be 101 different things between 0 and 1, right? Second example, actual population. Maybe our population is still all people in New York, but now we're talking about their average height. A very different kind of statistic, you see. In the previous question, we were... Sorry, I'm stifling a sneeze here, and I don't know when it's going to come out. In the previous question, we were talking about categorical data. Everybody was or wasn't left-handed. People you could or do pick, individuals, either are or are not left-handed, and we're tallying up proportions that are. That's how we're getting our number, proportion of yeses. Now we're talking about everybody in the population is a number, quantitative data. Everybody you could or do pick is a number, and we're averaging those numbers together. So it's a very different type of number, but it's still a number. So population, everybody in New York. Parameter, the average height of everybody in New York, which is what it is, right? And it can't be something else. The average height of everybody in New York State is 5.6 feet. That is either a true statement or a false statement. It is, I mean, either way, I mean, the average height of everybody in New York, that number, whether I ever know it or not, is what it is. The average height of 100 selected New Yorkers. Well, again, our sample will be 100 selected New Yorkers, and our corresponding statistic will be the average height of the 100 New Yorkers you pick. Now, everything that is common sense, and everything that we're going to do over the next few sections, and in fact the law of large numbers from section 5, tells us that the average of what we do pick will probably be close to the average of what we could pick. So if the average height of everybody in New York State is 5.6 feet, probably the average height of the 100 people we pick will be around 5.6 feet. But what if it's not, right? There are no guarantees. There's nothing in the world stopping you from picking the 100 shortest people in New York and getting something very small, 4 feet. or picking the 100 tallest people in New York and getting something very big, 8 feet. So the reality is that the average height of the 100 selected New Yorkers could be pretty much anything, right? I mean, between, let's say, 4 and 8 feet, whatever. But probably it'll be close to this. I mean, probably is a loaded word, right? What if it's not? So we'll worry about that later. Alternately, we could have a theoretical population, all possible flips of a coin, all possible spins of a spinner, all possible rolls of the die, any of those abstract probability situations that we've talked about. So maybe our situation is once again categorical, a coin that can be head or tails, and our population is all possible flips of a certain coin. If it's a fair coin, then half of them would be heads and half of them would be tails. But maybe it's not a fair coin. So the parameter in question would be the proportion of all possible flips of that coin that would be heads. Remember, this is exactly what we mean by the probability of a head. That was perspective 3 on probability from back in the day, right? So the proportion of all possible flips of a certain coin that would be heads. All possible flips is our population. The proportion of all possible flips that are heads would be our parameter. That is the probability of a head. For a fair coin, a half. For some other coin, 0.4. Who knows? Maybe it's a two-headed coin. Maybe it's 1. Maybe it's a two-tailed coin. Maybe it's 0. Without looking at the coin, who knows? Now we do a sample of 100 flips. Of course, you could get 100 heads, or you could get 100 tails, or anything in between. You probably won't, but you could. So the proportion of 100, so our sample in this case would be the 100 actual flips of the coin that we do. What you want to understand is that this distinction between an actual population and a theoretical population is no distinction at all, right? So much of what gives people problems is a failure to recognize this. There is no real difference between 100 flips of a coin picked from a population where 1/2 of all possible flips are heads, or 100 people who may or may not be male picked from a population where half the people are male. The only difference is one is an actual population and hence technically finite, billions of people, and the other is a theoretical population, all possible flips of a coin, all possible repeats of whatever random thing you're doing, is of course theoretically infinite. But what's the difference between theoretically infinite and 7 billion when you're doing 100? So it's a distinction without a difference. 100 flips, if you flip a coin 100 times, then what you are doing is you are picking 100 flips of the coin from the population of all possible flips, just as we were previously picking 100 New Yorkers from all possible New Yorkers. The fact that the one is finite and the other is theoretically infinite is neither here nor there. In both cases, there's a lot more than 100 out there. Okay, 100 flips of a coin, flipping a coin 100 times is picking 100 flips from all possible flips. It's just sampling. Now there is a difference there in the sense that any flip of a coin that you're about to do is kind of philosophically interchangeable with any other flip of a coin that you're about to do. But, you know, how do you pick things from the real world? What if you pick people coming out of a big and tall store? What if you pick people coming out of a left-handed store? We'll talk about those issues a bit later. With an actual population, the issue of how you pick is a little bit more interesting. But that's neither here nor there. 100 flips of a coin picked from all possible flips of a coin. So our statistic then would be the proportion of 100 actual flips that are heads. Let's say the coin is fair. Let's say that this parameter is 0.5. Let's say the coin is fair. Well, then 100 flips of a coin could be all heads, in which case this proportion is 1, or it could be all tails, in which case this proportion is 0, or it could be 30 out of 100 heads, in which case this proportion is 0.3. So effectively, this thing could be anything between 0 and 1. By which, again, I mean it could be 0 over 100, or 1 over 100, or 2 over 100, 101 different things between 0 and 1. Well, we talked about the difference between jaggedy and smooth, and so many bars that it may as well be smooth. So if you could be 101 different things between 0 and 1, then for all practical intents and purposes, you can be anything between 0 and 1. If that sounds familiar, it's because we're going to tie all this together as we go. And then finally, you could be talking about a quantitative theoretical population, the average of all possible rolls of a die. Well, we talked about that. For a fair die, 1, 2, 3, 4, 5, 6, it would be 3.5, right? The balance point of the die, as previously discussed in section 5, mu. Mu for the die, mu for the spinner, mu for whatever random thing you're doing, mu for the unfair 20-sided die, whatever. Any probability situation, the theoretical average of all possible repeats, the balance point, the mu concept from chapter 5, the balance point of possibilities. For a fair coin, again, that was 3.5. So our population in this case is all possible rolls of the die. And our parameter is the average of all possible rolls. Again, for a fair die, that would be 3.5. For an unfair die, it might be something else. For a die with 3 sides labeled 1 and 3 sides labeled 2, it would presumably be 1.5, and so forth and so on. But, you know, use your imagination. And then the 100 actual rolls that you do would be the sample, and the average of the 100 actual rolls that you do would be the statistic. The average of 100 rolls of, let's say, a fair die. Let's say this parameter is 3.5. Cube, 1, 2, 3, 4, 5, 6, fairly balanced. Balance point, 3.5. Well, even so, 100 rolls of a fair die could average up to, well, pretty much anything between 1 and 6, right? Because 100 rolls of a fair die, or any die, as long as, you know, it's labeled the right way, 100 rolls of a fair die could give you anything, right? You could get all 1s, in which case they average up to 1. Or you could get 50 2s and 50 3s, in which case they average up to 2.5. Or you could get 50 5s and 50 6s, in which case they average up to 5.5. Or you could get 99 6s and 1 5, in which case they average up to, figure it out, 5.9 something. So if you think about the number of ways that 100 numbers, each of which is 1 and 6, 100 numbers, each of which is 1 or 2 or 3 or 4 or 5 or 6, you know, a string 100 long of 1 through 6s. If you think of the different things they could average up to, well, there's no words for how many different averages you could get there, but a lot of them. So you could get a lot of different numbers, technically finite. How many ways could 6 different numbers, how many ways could 100 numbers, each of which is one of 6 different things, how many different averages could you get? Well, it's technically finite, but I'm sure it's very, very big, millions. So for all practical intents and purposes, you can get pretty much anything between 1 and 6, right? When you average together 100 rolls of a die. It could be 1 point anything, or 2 point anything, or 3 point anything, or 4 point anything, or 5 point anything, or actual 6 if it's 100 6s. But of course, if you roll a fair die 100 times, you're almost certainly not going to get 100 6s. You're almost certainly not going to get 50 2s and 50 3s. So you've got an idea what's going to happen. You'll probably get close to 3.5. And again, that is the law of large numbers. The average of what you do pick particularly as you average more and more of them together, and 100 is relatively big. The average of what you do pick will probably be close to the average of what you do pick. So once again, this is an X bar kind of thing, the average of 100 actual numbers. This is a mu kind of thing, the balance point of all possibilities. Just as in the actual population, this is an X bar kind of thing, the average of 100 numbers. And this is a mu kind of thing. It's a more abstract mean, the average height of everybody out there. Too much to be data. The distinction becomes very important, remember. X bar, data average. Mu, an average that's a bit more abstract or theoretical. Now, the average height of everybody in New York is not abstract in quite the same way that the average of all possible rolls of a die is, but they're both out there somewhere, right? They're too much to be data, so they are not explicitly computed from data. They're mu's. In both cases, whether it's all possible rolls of a die or all possible New Yorkers, we're talking about the average of what you could pick. That's a mu type of thing. X bar, the average of what you do pick, that's the statistic. So we'll tie all this together. The actual versus theoretical population is a distinction without a difference. Big thing to get through your head. There's no difference, really. I mean, we've got different rules, obviously, for height that we do for a die, but picking 100 rolls of a die from all possible rolls of a die is the same kind of thing as picking 100 people from all possible people. The difference is you can be a lot more heights than just 6 different heights. The rules are very different. So how do we actually pick? Well, let's focus more on the actual population, because 100 rolls of a die you're about to do, 100 flips of a coin you're about to do, are pretty much philosophically interchangeable with any other 100 flips of a coin that you're about to do, right? The issue of how you pick kind of takes care of itself. But for an actual population, you could be picking people in Las Vegas coming in and out of a hotel during a left-handed convention, or you could be picking people in the neighborhood of a big and tall shop. Use your imagination. There are all kinds of ways that you could pick. So when you're picking actual people or things, you could be picking 100, if you're talking about the calculators in the warehouse, you could be picking 100 calculators. You could walk in the door, pry open the nearest crate, and pick so many calculators off the top of the first crate that you happen to see coming in the door. Why is that a bad idea? Well, we'll see, but common sense tells you that if the machine breaks down, probably all those calculators are going to go the same way, right? So it's not going to be representative necessarily. Now, there's no guarantees the sample is representative, but there are certainly bad ways of going about it. There are ways of cursing yourself at the beginning, and we want to avoid those. So this gets into the whole issue of how we pick. How do we choose our sample? Well, randomly, of course, right? But that's not an answer, right? Everything that we did in section 5 and 6 was the big takeaway from section 5 and 6. The big conceptual takeaway from sections 5 and 6 is that randomness always has a pattern, right? You can randomly pick people's incomes, but you're probably going to get a low one. Right skewed. You could randomly pick people's grades, but you're probably going to get a high one, left skewed. You could randomly pick people's heights, but you're probably going to get something central, unimodal, symmetric, and so forth and so on. You could randomly pick a roll of the die, and you're just as likely to get anything as anything else. Randomness always has a shape. That's the big takeaway. Even when things are random, there's always a probability distribution in play. You could randomly pick name, assuming there are still phone books, you can randomly pick somebody's name out of the phone book. But one thing's for sure, you're going to be picking people whose names are in the phone book. and so forth and so on. You could randomly go to people's doors and ring their doorbells to ask them questions, but one thing's for sure, they live in a house, and so forth and so on. So you do have to be very careful how you pick. So, with all that in mind, the concept of a simple random sample. A simple random sample of size n. Well, first of all, we are picking randomly, but again, that is no answer. To say that you pick something randomly is not very specific. There are all kinds of patterns of randomness. You can randomly pick people in Las Vegas during a left-handed convention. You could randomly pick people going in and out of theaters in July to ask them whether they like action movies. At least you used to be able to. So you see, there are any number of ways of rigging the game. Now again, mine is not to judge you. Either you are going about it poorly, or you are very creatively trying to get the answer that you want to get. There's a good living in that, I'm told. But you're not really doing what you're claiming that you're doing. So we do have to be a little bit more specific about this. So we know what a sample is. We know what it means in a general way to pick randomly. What is the simple part telling us? And of course we know what size n means, of course. Size 100 people or things. A simple random sample, SRS for short, because we use it a lot. A simple random sample of size n. Now, this is a little bit wordy to say properly, but it's an easy enough idea to understand. I have pared it to the bone here so that it's a little easier to follow, but in all of its verbosity it goes something like this. A simple random sample of size n consists of n individuals picked from the population in such a way that every group of n individuals that you could pick has an equal chance of being selected. I'll say that again. A simple random sample of size n consists of n individuals picked from the population in such a way that every group of n individuals you could possibly formulate has an equal chance of being selected. Every possible sample of size n has the same chance of being picked. So a simple random sample of 100 New Yorkers, for instance, means that in your mind's eye, formulate every possible group of 100 New Yorkers that could possibly be formulated. Which is a technically finite number of groups, but that's neither here nor there. Every one of those groups has an equal chance of being selected. So in a general way, we're saying that some types of groups don't get preferential treatment. Some types of groups don't have a bigger chance of being selected, or a smaller one, and so forth and so on. Now, this is an ideal, obviously. You can't wrap your mind around every possible group of 100 New Yorkers, let alone check that they're all equally likely. It's an ideal. It is what we shoot for. There are obvious ways that it can go wrong, and we'll talk about that. What we shoot for, the ideal for which we shoot, is the presumption that we have good cause to believe that we have a simple random sample. It's not the kind of thing you could ever know for sure. And by the way, if you are capable of wrapping your mind around every possible group of 100 New Yorkers, congratulations. That's 1,000 times. That is unthinkably harder than just asking everybody in New York whether they're left-handed or what their heights are, which was supposed to be impossible in the first place, right? So it's not doable. It's an ideal. It's something that we have reasonable cause to believe could be the case in the real world. There are ways of minimizing the risks. There are ways of avoiding the things that are obviously going to screw up this. But it's not the kind of thing you could ever know for certain. It's an ideal. And by the way, what am I not saying? I am not saying, for instance, divide the population of New York into groups of 100 and pick one. The word there would be partition. I'm not saying divide the population of New York into groups of 100 and pick one. That's a lot of groups. I'm saying something unthinkably more complicated than that. I'm saying every possible group of New Yorkers. So if you're a New Yorker, then you're in some of those groups and you're not in some of those groups. Most of them you're probably not in, but a lot of them you are. So every possible group. Now 100 flips of a coin that you're about to do, or 100 rolls of a die that you're about to do, or anything theoretical of that nature, pretty much fulfills this by default, right? 100 flips of a coin that you're about to do are philosophically interchangeable with any other 100 flips of a coin that you're about to do, and they've, in some philosophical sense, got an equal chance of being selected, right? So the simple random sample thing is pretty much taken for granted in a situation like that. It's got more to do with when you're picking things from the real world, an actual population. It's an ideal, as I said here. This means, by the way, that for every unusual sample you might get in one direction, there's a counterbalancing sample in the other direction that you're just as likely to pick, right? For instance, you could get 100 ones, but on the other hand, you are just as likely to get 100 sixes, right? For every group of 100 ones out there that exists, there's a group of 100 sixes out there that exists, and everything balances, right? For every group of 52s and 53s, there's a counterbalancing group of 53s and 54s. Now, that's a little abstract, but it's probably easier than doing it for the actual population. Let's give it a go. Let's take this example. So for every group out there that consists of 100 left-handed people, there's a counterbalancing group of 100 right-handed people, and so forth and so on. Now, before you could say that there's a lot more groups of all right-handed people than there are groups of all left-handed people, and that's certainly true, the word here is balance, not symmetry. Counterbalancing. So it's a little trickier in an asymmetrical example like this, but it does all work out in the end. Counterbalancing. Take something a little bit maybe easier to wrap your mind around. Let's say that the average height of all people is 5.6 feet. Now that's something that's probably reasonably symmetric, so it's a little easier to wrap your mind around. For every group out there where the average height is 5.5 feet, there's a counterbalancing group out there that you're just as likely to pick where the average height was 5.7 feet, and so on and so on. What'd I say, 5.6? So for every group out there where the average height is 5.59, there's a counterbalancing group where the average height is 5.601, and so forth and so forth and so on. For every group out there where the average height is half a foot under 5.6, there's a counterbalancing group where the average height is half a foot over 5.6, and so on and so on and so on. Now again, this is a little harder to wrap your mind around, but even for something skewed, whether it's right skewed like this, or sort of categorical, there's more right-handed people than there are left-handed people, even for something that's asymmetrical like that, the word is balance, not symmetry. So this is just a way of thinking about it that'll make it easier for you. Summarize it by saying what I say here. For every unusual sample you might get in one direction, there's a counterbalancing sample unusual in the other direction that you're just as likely to pick. Yes, you might get a weird sample, but in probability terms, it could just as likely been just as weird in the other direction. So the upside of the simple random sample is that everything balances nicely. And for every unusual sample that you're likely to get in one direction, you're just as likely to get an unusual sample in the other direction. In the long run, everything balances properly. The downside of the simple random sample is, what about the actual one sample that we're going to do? We're not going to do lots of samples, let alone look at how they balance. You're only going to do one sample. So what if you get a weird one, right? Every possible sample of size n has the same chance of being selected. So there's no reason in the world you couldn't select 100 ones, or 100 heads, or the 100 shortest people in the country, or 100 left-handed people. So yes, you could get a weird sample. It is entirely possible. There are no guarantees. The sample you've just done might be very weird, but sample for sample for sample in the long run, its weirdness is balanced out by some other sample's weirdness that you could just as easily have got. Now, there is no long run with samples. We're only going to do one, but it's an ideal. Remember, we're still in sections 7, 8, and 9 talking about the theory of statistics, not actual sampling. In the real world, sections 10 onward, you're only doing one sample, and you've already got your answer. We'll worry about that later. In the theory of statistics, a simple random sample says that every sample that is weird in one direction is counterbalanced by a sample that's weird in the other direction. What this means we'll see as we go on. Now, there's all kinds of other ways you can sample. There's cluster sampling, there's stratified sampling, and so forth and so on. And we're not going to talk about those, but you can read about them if you're interested. Trying to remember, stratified sampling, I think it was the one that went wrong in the famous Dewey versus Truman polls, among other things. If you've ever seen that example of Truman holding up the newspaper that says Dewey defeats Truman. So yes, sampling can go horribly wrong. And never forget that pollsters, like everybody else, have a pack mentality. They all tend to be using the same methods at the same time. Whatever happens to be mathematically fashionable, and so forth and so on. And that's neglecting all the moral issues involved, all the ethical issues involved, even under ideal conditions, which are rarely achieved. Pollsters still have a pack mentality, and that's exactly what went wrong in the Dewey versus Truman polls, is that everybody was polling the same way, and the conditions that they were trying to achieve were ridiculously arcane. They were looking, when they were polling, they were looking for a certain proportion of blue-eyed female farmers between the ages of 18 and 20 and so forth and so on, and that did not end well for them. It doesn't pay to get too clever, and certainly not in a course called Elementary Statistics, so we'll keep it simple, although the book will go into painful detail for the reasons we've talked about. Nevertheless, we'll just stick to a simple random sample, and again, even that will be an ideal. There are things to avoid if you want to, there are obvious things to avoid if you're trying to achieve a simple random sample. There are less obvious things to avoid, but it remains an ideal. It remains something that you would never actually verify. Except, of course, you know, in these theoretical situations where you kind of take it for granted. Let's see, I'm just thinking ahead to where I want to end this particular video. I think I'll finish off this page. Notice for future, now this has nothing necessarily to do with anything we're talking about at this exact point, but this is a good place to mention it. Notice for future reference that there is a big difference between something being unknown or known versus something being random or being a fact. To be random is a situation we've talked about since section 4 and even previously. To be random means you can repeat under, quote, seemingly identical conditions, unquote, and don't get too clever about that, we talked about. To be random means that you can repeat something under identical conditions and get a different answer. You know, one flip of the coin, next flip of the coin, random. One roll of the die, next roll of the die, random. height of the person you pick this time, height of the person you pick next time. Random. Now, if the flip of the coin is in your future, then it's random whether the coin will land heads or tails. Simple, right? If you have just flipped the coin and gotten a head, and you can see that, then it was going to be random, but now it's a head. That's important. Any piece of information you get from the random sample that you happen to do has to take into account that you could just as easily have gotten a different sample. Even if it's as simple as a sample of one flip of a coin. Yeah, you flipped the coin and got a head, but if it's a fair coin, you could just as likely have gotten a tail. Yeah, you rolled the die and got a 3, but you could just as likely have gotten a 4, or a 2, or a 1, or a 6, or whatever I've forgotten, a 5. So you want to be very careful about that. To be random means that you can repeat and get a different answer. If the random thing is in your future, a flip of the coin that you're about to do, then the result is unknown. If the random thing is in your past, you have just flipped the coin, you've just spun the spinner, you've just rolled the die, you've just picked the person and gotten their height or whatever, then it was still random, but now you know what it is, right? You are still talking about a random phenomenon, but whether you know the answer or not depends on where you stand. Future, you don't know it. Past, you know it. Whether something is random or not has nothing to do with whether it's known or unknown. On the other side of things, whether something is known or unknown has nothing to do with whether it is random, right? The typical way we do this is that you know whether the coin is fair or not, you know what proportion of people out there are left-handed, and then you pick or do 100 of them, and you're going to get what you're going to get. So that for the time being, when we're talking about probability, the rules, the governing principles, the populations are known. 50%, you have a fair coin. 50% of all possible tosses of the coin is fair. For the sake of argument, 10% of people in New York are left-handed. For the sake of argument, the average height of everybody in the United States is 5.6 feet, etc. You know the rules, and you're about to pick or do 100 things, and you don't know the random thing you're about to get. So when you're doing probability, it's the rules that are known, and it's the result of the randomness in your future that is unknown. But don't forget, our goal is not this stuff. Our goal is actual sampling, starting in section 10. This is just theory of statistics, not practice. In the real world, you never know whether the coin is fair. In the real world, you never know what proportion of all people in New York are left-handed. In the real world, you never know the average height of everybody in the United States, etc., etc., etc. And you try to wrap your mind around it by polling 1,000, whatever. Sampling 1,000 and getting what you get. So in the real world, you have just sampled 1,000 people, and their average height was whatever, or 10% of, or 11% of them were left-handed, and so on and so on and so on. The random thing is a fact. It is, you know what, sorry, take that back. The random thing is known because it is in the past. You have done it. And you don't know the parameter, you don't know the rules, the governing principles, you don't know what proportion of all people in the world are left-handed, you don't know the average height of everybody in New York State, and you never will. So, but there's nothing random about it, right? The average height of everybody in New York State is what it is. You cannot repeat with a different New York State and get a different average height of everybody in New York State. There is nothing random about the average height of everybody in New York State. There is nothing random about what proportion of people in the United States are left-handed. There is nothing random about what proportion of all possible tosses of a coin will land heads? What is the probability of a head for that coin? Well, it is what it is. The average height of everybody in the world is what it is. The proportion of left-handed people in the world is what it is, and it can't be something else. You can't repeat with a different world and get a different answer. Simply being unknown does not make something random. Let me repeat that. Simply being unknown does not make something random. Parameters, rules, governing principles are facts. They are what they are. There's nothing random about them. There's nothing random about the proportion of New Yorkers who are left-handed. It is what it is, and it can't be something else. There's nothing random about the average height of all New Yorkers. It is what it is and can't be something else. There's nothing random about what proportion of all possible flips of a coin will be heads. There's nothing random about the probability of a head for that coin. You know, if it's a fair coin, it's a half. If it's some other coin, it's 0.4, and so forth and so on. There's nothing random about the balance point of a die. If it's a fair one, 3.5. If it's weighted in some other way, some other number. But it is what it is. What is random? The statistic is random. Parameters are facts, whether you know them or not. You may or may not know the proportion of all New Yorkers who are left-handed. In these type of problems, in the middle of the course, we presume to know it for the purposes of studying what a sample is likely to do. But ultimately, we turn it around, right? In later sections, we've done the sample, and we never know this highlighted thing. We're trying to do the sample precisely to wrap our minds around this, and so on and so on. We use statistics to estimate parameters, but that's still in our future. For the time being, we know the parameters, and we're looking at the probability distributions of the statistics. We're looking at what pattern of randomness a fair coin flipped 100 times has. What pattern of randomness 100 people picked from New York State has vis-a-vis left-handedness, and so forth and so on and so on. So, parameters are facts. They are what they are, whether you know them or not. Whether you know them or not depends on where you stand. For the sake of argument, you have a fair coin, known. How do you ever know that a coin is fair? Well, you don't in the real world. So you may or may not ever know the parameter, but that has nothing to do with randomness. Parameters are not random. They are facts. Whether you know those facts or not, whether you know the average height of everybody in the world, it is still the number it is, and it is not going to change. Statistics are random, right? Well, obviously, if you randomly pick 100 people or things, or randomly flip a coin 100 times, that is, do that random thing, or randomly pick 100 die rolls, or randomly pick 100 New Yorker, well, random, right? So, random. Statistics are random, whether you know them or not. If the height of if the 100 people you're going to measure in your future, then their average height is not known. If the 100 people you have just measured is in their past and you've computed the average, then it is known. But it was going to be random. Why is this important? Because the latter part of the course is philosophically confusing. The goal is to get all of the math out of the way in sections 7, 8, and 9, so that the only thing that really remains in the later sections will be the weirdness about thinking about everything backwards. When you are thinking about the randomness of things that have already happened, that is a little philosophically weird. So we'll worry about that starting in section 10. Just things to be aware of. Parameters are facts, whether you know them or not. Statistics are going to be, or were, random, whether you know them or not. It's a very important distinction, and I think this is basically what I do here. And here. So once again, probability argues from the known fact to the unknown sample that we're about to do. For the sake of argument, a coin is fair. Parameter, half of all possible tosses are heads. The probability of a head is a half. What's the probability that less than 49% of the next 1,000 tosses will be heads? Well, we'll talk about that in Section 8, but notice the way it's worded. You know the rules, you know the governing principles, you know the parameter. We are looking at the probability that the sample in the future will be this, that, or the other. That's probability. That's Sections 8 and 9. Later on, Section 10 and forward, using probability in a practical way. Statistics takes probability and throws it into reverse. Statistics argues from the statistic you've done, which was random and therefore could have been something else, to the unknown parameter. 480 out of 1,000 tosses of a coin were heads. Is it plausible that the coin was fair? 12 out of the 100 people we've just looked at were left-handed. What proportion of everybody out there is left-handed? Is it plausible that it's 10%, for instance? Those are the kind of questions that we'll be looking at in future sections. And again, it's very philosophically weird. It's a little bit hard to think backwards. Statistics is probability done backwards. You know the result of the random thing you were going to do, and you want to conclude something about reality, the nature of the coin, the fact. For instance, we would never say that, based on what I've highlighted here, we would never say that the probability we would never say that the probability that the coin is fair is whatever. There is no probability that the coin is fair. The coin is either fair or it's not. Based on the sample we've just done, what's the probability that the average height of everybody in the United States is 5.6 feet? It's meaningless. Either it is the case that the average height of everybody in the United States is 5.6 feet, or it is not the case. It's either a fact or it's a falsehood. There's nothing random about it. You can't repeat with a different United States and get a different average height. There's nothing probably about a parameter. They are what they are, whether you know them or not. What is probably is what you happen to have done. The average height of the people you happen to look at, that was a probably. The 480 out of 1,000 tosses of a coin being heads, that was a probably. In other words, anything that you are going to conclude about the nature of the coin based on this fact, based on this sample, has to take into account the fact that if you flip the coin a different 1,000 times, you're almost certainly not going to get this, right? You'll get something else. So you've got to be very careful about what you conclude from a sample. Okay, 510 of the 1,000 people I just looked at say they're going to vote for so-and-so. Well, what's going to happen on the next 1,000 people I look at? So you've got to be very careful. Anything that you conclude from a sample has to take into account the fact that you could just as easily have gotten a different sample. Now that is philosophically weird, and we'll worry about it starting in Section 10. But probability for all of its sins is relatively straightforward. And that, in other words, we're not doing things backwards. So for that reason, Sections 8 and 9 are a little bit easier philosophically than what we do later. But again, the goal is to get the math out of the way so that the only thing that remains is the philosophical weirdness of the later sections. And with luck, the math will be old hat by the time we get there. So that way you're not hit with everything at once. Sections 7, 8, and 9 have to do with sampling. Sections 7, 8, and 9 have to do with, well, 8 and 9 in particular, have to do with sampling distributions, patterns of randomness for different types of statistics. Before you conclude anything from 1,000 flips of a coin, 480 of which were heads, you have to understand the pattern of randomness for a fair coin flipped 1,000 times. Otherwise, you've got no context for this guy. Okay? So, theory in sections 8 and 9. patterns of randomness? Well, the bottom line, of course, is that a statistic is a number that results from doing something random, right? So a statistic is a random variable, and therefore it has a pattern of randomness. It has a shape to its randomness, a center, and a spread, and all of this ties right back to what we did in sections 5 and 6. So that's how all this stuff begins to come together. We'll continue on by doing an example of these ideas in the next video. This is probably going to be on the long side. It's not a complicated section, but I want to take it slow because it is an important one. So continued section 7 next time.